it's so cool that you think about morals and aesthetics and philosophy. And I'm curious, when did that start?
I think it probably safe to say that it started when I was an undergraduate. I was an undergraduate at Villanova University, a good Catholic school where they forced you to take a whole bunch of classes far outside your major. So every liberal arts undergraduate, liberal arts and sciences undergraduate, had to take 3 semesters of philosophy, in addition to 3 semesters of religious studies and 3 semesters of history and 3 semesters of English all down the line. So that's where I first took a formal philosophy course, and I did fall in love with it right away. I didn't, and ended up being a philosophy minor. I didn't ever think that it would have something to do with my work in physics. That wasn't until much later, till I was a professor, a junior faculty member, that I realized that some of my work in cosmology had a very direct overlap with people in philosophy departments who worked on what they called foundations of physics. So rather than arguing about Karl Popper type stuff, what's a theory, what's not a theory, they were really doing physics, but they were just doing physics in a way that would only get them hired in philosophy departments.
Oh,
So
that's super interesting.
yeah, so those are my people.
Wait, you have to explain more. What is meant by that? They're doing foundations of physics, but if for some reason would only be the job placement was only in the philosophy department.
Well, think about the arrow of time, which is where I was actually working on this particular thing. So I didn't get into quantum mechanics until somewhat later. So thinking about why the past is different from the future, it goes back to Boltzmann and Maxwell and other people, because they're the ones who invented the problem. The problem didn't exist before them because there just was an arrow of time. The past was different from the future. It only became a problem when you invented these mechanistic kinetic theories, where you said that heat is the kinetic energy of molecules and entropy is the number of ways you can arrange them, etc. So basically, you're reducing everything to particles obeying Newton's laws. And Newton's laws don't have an arrow of time in them. And so if you're reducing everything to particles obeying Newton's laws, now you have a problem that you didn't have before. Why is there an arrow of time? And there's a long tradition in physics, going back to Boltzmann, of claiming that you have derived the arrow of time when you really haven't. You've cheated, you put it in your assumptions, and you derived time asymmetric conclusions from time asymmetric assumptions, which is not very difficult to do. And it was the philosophers who really figured this out and got it straight. And I think that in the philosophy of physics community, foundations of physics community, David Albert at Columbia is given the most credit for really sort of establishing what is thought of as the conventional picture, where you give equal credit to the dynamical laws and to the initial conditions. And again, plenty of people had sort of said words like this. Richard Feynman, Arthur Eddington, plenty of people, have thought about this, but it was the philosophers who really said it clearly and rigorously and so forth. Meanwhile, in physics classes around the world, we're still told that you can derive the second law from some equations without putting in an initial condition explicitly. And that's just wrong. We're just lied to, but that's okay because you get the right answer. And physicists at the end of the day just want to get the right answer, which is that entropy increases.
What was wrong with Boltzmann's argument? And what's meant exactly when you say people should give, or that David Albert showed that people should give equal credit to initial conditions and evolution laws?
So the idea that Boltzmann had was that you could start with, and again, not only Boltzmann, but others, you could start with this idea that a gas is actually a bunch of, let's say atoms bumping into each other, okay? And then you can just use probability and statistics to derive the idea that entropy increases. And he indeed did prove a theorem, the H theorem, that kind of sounds like that. But it makes an assumption, the assumption of what is called molecular chaos, in German, the Stoßzahlansatz. And the molecular chaos assumption says that if I have a bunch of molecules going to bump into each other, they are uncorrelated with each other, okay? Which kind of makes sense. They're moving around randomly in the box of gas, etc. But it turns out at the technical level, you can make that assumption once. But as soon as you make that assumption at one moment of time, then when the molecules bump into each other, now they're correlated. now they're coming in opposite directions from where they were before, right? So you can't remake that assumption again and again. So either there's you have a choice of two possible mistakes. One mistake is you remake that assumption again and again, and that's usually what people do because it gets them the right answer. Or you just apply it at the beginning of your problem and not the end. The reason why that's a mistake is because you're trying to derive the fact that there's a difference between the past and future. And if you assume there's a difference between the past and the future, then you haven't really succeeded, right? And look, again, people are smart. Loschmidt pointed this out to Boltzmann. Loschmidt had been Boltzmann's professor. And, Boltzmann kind of filibustered. He never came up with a good answer to this so-called reversibility paradox. And ultimately, the answer is you have to explicitly break time reversal symmetry by putting an initial condition that is low entropy.
So what do you make of approaches that do away with initial conditions or boundary conditions like Hawking and Hartle? And for people who are listening, when they hear Hawking and Hartle, no boundary, and they think in terms of you have an equation and you input something in, the equation's the black box, and you output, it sounds like there is no input. How can you even have an output? What does that look like? Help people understand that.
Well, so there's two things. Number one, Hartle and Hawking have what is called the no boundary proposal for the wave function of the universe, but it's certainly an initial condition. They certainly apply it at the beginning and not the end. It's called the no boundary condition for technical reasons in quantum gravity. So let's indulge our readers with some technicalities for 30 seconds, and then we'll pull back. Feynman told us that we can do quantum mechanics by doing a path integral. That is to say, by summing up contributions from every different possible trajectory the system can take. In this case, because we're doing gravity, the trajectories a system can take are geometries of space-time. Okay, so you would like to sum over every geometry of space-time. That's hard. So the first move that Hawking makes is instead of summing over every space-time, let's sum over every space. So let's just imagine that there was no time dimension and just treat everything in a Euclidean way, as we say, but we let it be curved. And then if you have some state of the universe at one moment of time, you can sum over all of the Euclidean continuations of that to the past that don't have another boundary. They have the boundary that is the moment of time you're looking at, but no previous boundary. And that's the no boundary wave function of the universe. Now, if that's all you ever did, that would be cheating just as much as Boltzmann did. You're putting in an arrow of time. In later years, Hartle and Hawking, and also Thomas Hertog, who wrote a book about this not too long ago, who's their collaborator, they talked to people like me and David Albert and other people who cared about the arrow of time, and they realized that they need to be a little bit more careful about what their assumptions were. And it actually goes back to an even earlier debate between Stephen Hawking and Don Page in the pages of Nature and so forth. But the result is that they now would like to claim that the set of all solutions to their equation is completely time symmetric. But we live in a solution that is not. And that's actually a very sort of plausible, clever possibility to think about. I think it's very alive, but I think that, again, quantum gravity is too hard for us to say anything definitive about it one way or the other. Others, like myself, have other theories where you don't really focus on the quantum state of the universe. You have a universe that is largely classical, but is also symmetric between the past and future. And the real difference is that we don't see the whole universe. So in our picture, what you and I think of as the Big Bang is not the beginning of the universe. It is the emergence of our little bit of universe out of some pre-existing thing. And the whole shebang is actually symmetric in time. So again, not cheating the way that Boltzmann did.
That's a great word play. The whole shebang versus the Big Bang.
Yep.
So can you explain how is one supposed to think of the whole shebang compared to the Big Bang? And are you saying that our experience of the arrow of time is somehow some local phenomenon?
It's absolutely, in my picture, some local phenomenon. The whole shebang is just a fancy, a casual word for the multiverse, right? The idea in cosmology of the multiverse is that there are regions of space and space-time that are just far away in either space or in time, so we can't see them, where conditions are very, very different. And so in our picture, that includes not just far away in space, but even before the Big Bang as well. And again, plenty of other people have theories of things that happened before the Big Bang. But except for our model, I think this is still true, they do one of two things. Either they put in an arrow of time forever so that there is some directionality to the time evolution of the universe. For example, Penrose's conformal cyclic cosmology does that. Or they treat our Big Bang as a special moment, as a moment of special conditions, low entropy, for whatever reason, because it fits the data or whatever, which is also perfectly fine. But in both cases, you're not explaining the special condition of our early universe. You're putting it in some way. Our ambition is to not make any assumptions about the speciality of the state of the universe at any one moment of time, and to argue that in almost any initial condition, you can go both forward and backward in time and get a universe that ultimately looks like ours.
So that's an explanation, whereas sometimes people would say, we explain the fact of fine-tuning because everything happens, and then there's the anthropic argument. So what you're saying is not the anthropic argument.
Ours is anthropic only in the following sense. In our whole shebang, the vast, vast majority of places to live have no matter in them, have no matter or energy, it's just empty space. So, of course, we're not going to find ourselves there. We're going to find ourselves in hospitable regions of space-time. So that's anthropic in exactly the same way that we explain why we live on the surface of the Earth rather than on the surface of the sun. There's a lot more surface to the sun than the Earth, but it's not a hospitable place to live, so we're not surprised that we find ourselves here.
This was just a teaser. The full podcast is in the description. As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.